Welcome back everyone. In the last session, we have constructed cluster expansion model for the lithium nickel oxide. Today we will go a step ahead and perform Monte Carlo simulations for the same structure. Okay, we will simulate lithium intercalation and deintercalation in a layered lithium nickel oxide structure using a semi-grand canonical Monte Carlo approach. Okay, one thing to note that this lithium nickel oxide system exhibits Coplot disorder. What that means? It means it has both in the lithium sublattice it can have lithium positive or the vacancy, and on the nickel sublattice it can have Ni3 positive or Ni4 positive. Okay, this exchange of Li positive or vacancy corresponds to charging and discharging, while as Ni3 positive, Ni4 positive reflects the redox response of the host lattice. So basically we will use Monte Carlo sampling to explore how the energy and composition of the system changes in response to the varying chemical potential of the vacancy. Let us get started. So in this notebook we will load a trained CE model for the LNO. So we have previously obtained the CE model here, we will load that model here. Okay. Then we will initialize a semi-grand canonical ensemble with relative chemical potentials. Okay. Then we will create a random disordered configuration as a starting point. Okay. Then we will perform Monte Carlo sampling while sweeping the chemical potentials of vacancy species. Okay. Then finally we will analyze the resulting lithium ion concentration and total energy as function of vacancy chemical potential. Okay. Let's now import some important libraries here such as NumPy, JSON, and we also import structure from the PyMargin and also the species from the PyMargin, and for the plotting purpose we will use matplotlib.pyplot. Okay. Let us execute this cell. And also as you know, previously in the previous session we have got the cluster expansion model for the lithium nickel oxide, and we have saved that work in this file. Okay. Let us load this model here. Okay. Let us now construct a semi-grand ensemble. Okay. We will create a semi-grand ensemble. Okay. If we see here, we have imported ensemble here and we have defined a simulation matrix here. Okay. Other thing is we have defined chemical potentials also for all species as 0 for now, and we have instance of this class, that is ensemble class, with the parameters such as SC matrix defined earlier here and the chemical potentials. Okay. If we execute this cell, as we can see here we have printed the supercell size is 16 prims. Okay. What this mean? We have used 16 prims for the to perform Monte Carlo simulation. As you already know, we have constructed our cluster expansion model with the prim structure. Okay. For the Monte Carlo simulation we have to create a supercell. Okay. That supercell has 16 prim structures within. Okay. Now let us create a MC sampler. What is MC sampler? A sampler will take care of running sampling runs for the given ensemble. Okay. If we see here, we have imported sampler from the small.moca. Okay. We have created an instance of sampler class. Okay. We have defined temperature as 500 Kelvin. Let us execute this cell. Now let us create an initial structure and get occupancies. What is this here doing? In any Monte Carlo simulation, you initialize with some random configuration. Okay. you initialize with some random configuration, then you do some perturbation to that system, to that configuration. Okay, when you do some perturbation to that configuration, you compute the energy of the new configuration. Okay, you compute the energy of new configuration by your cluster expansion model, then you either accept that configuration or reject that configuration based on some criteria. Okay, so in this cell we are creating that initial structure. Okay, this is totally random structure. Let us execute this cell also. You can also print the encoded occupancy of this initial structure. Now, using a semi-grand canonical ensemble, we can sweep through relative chemical potentials and get average energies at various compositions. Okay. So, here we will sweep only relative chemical potentials of vacancies. Okay. We have defined our simulation cell. Now we will define the chemical potentials also here. We have defined range of chemical potentials here from 0 to 10 with the step size of 0.25, and we have defined some parameters, that is discard thin by is equal to 50, 10. What is thin by? Thin by means every 10th accepted configuration is stored. Okay. And the discard means number of initial stored samples to ignore when computing averages, and we are storing those averages here, concentration average and the energy average. What is this doing here? So, in any Monte Carlo simulation, when you access many configurations, okay, you get the energy of every configuration. When you accept it or reject it, you get the energy of configurations. Then at the end you take the average of those quantities. Okay, say formation energy, say composition, or you measure any other quantity. Now let us initialize here with the chemical potential of vacancy as 0. Okay, for now we will perform Monte Carlo simulation with the chemical potential of vacancy as 0. Okay, and here if we see this the sampler dot run, we have defined parameters such as 10,000. So, it is the number of steps, okay, number of Monte Carlo steps, and the initial occupancy also we had defined earlier, and parameters is equal to thin by also we had defined earlier. Okay. If we execute this cell, so it has run. Now, if we see the concentration average here of all the species, now you can see here the concentration of vacancy is 0. Okay. Concentration of lithium, nickel 3 positive is 0.25, nickel 4 positive is 0 again, and species such as species O2 minus, it has a concentration of 0.5. So, even we have initialized our Monte Carlo simulation with some random configuration. Okay, and obviously that random configuration it has no bias for any lithium positive, nickel 3 plus or Ni4 plus and vacancy. Okay. So, the random configuration likely contains an arbitrary non-charge balanced mix of lithium positive, nickel 3 plus, Ni4 positive and vacancies. Okay. We randomly assigned occupancies without considering the electrostatic or redox constraints. Okay. So, we have initialized our Monte Carlo simulation with some random configuration. There is no bias for any species. Okay. So, when we begin the Monte Carlo run with the chemical potentials of all species as 0, so there is no chemical potential bias favoring one species over another. Second, the system explores configuration is based solely on the cluster expansion model. Okay. The CE model trained on DFT data typically captures fully lithiated structure, that is LiNiO2, with only Ni3 positive ions energetically favored at 0 external bias. Okay. So, that is why the Monte Carlo naturally converges the configuration closed fully lithiated discharged state of the battery. Okay. Why this happens here? Because the fully lithiated phase is most energetically favored state, and there is no driving force to form lithium vacancies. Okay. So, the chemical potential of Ni3 positive is equal to Ni4 positive. There is no bias between Ni3 positive and Ni4 positive. Okay. However, C favors Ni3 positive rich configurations at high lithium ion concentrations as seen in DFT training data. Okay. If we see here, we can also print total energy versus steps here, execute this cell, and if we see as we run the number of steps, okay, as the simulation here runs, the energy, total energy comes down, it decreases with number of steps. Okay. We can also plot lithium concentration versus the steps. Okay. Execute this cell here, and if we here again you can see as we increase the number of steps here, okay, as the simulation runs, the lithium concentration also increases. Okay. Say this is initially some 0.14, then it is 0.25. Okay. Now we have done the Monte Carlo simulation at one chemical potential value. Okay. Let us now sweep through rest of the vacancy potentials. Okay. Here we can see we have defined for loop here. Okay. We have also defined this sampler dot run with the settings again 10,000 Monte Carlo steps here, thin by is equal to thin by, and progress is equal to true. Okay. Let us execute this cell. So, this cell will sweep through rest of the vacancy potentials. Okay. The simulation is complete now. We can also see the concentration averages here of all species. If we see the concentration average of all species, we can see the vacancy initially had vacancy as had the concentration of 0 here. Okay. Then it is 0.00081. Okay. And if we see the final concentration of this vacancy is 0.25. Okay. And the lithium has 0 concentration. We can also plot lithium concentration versus average total energy, and we can see here as the lithium concentration increases, energy also decreases. Okay. So, in this hands on session we have simulated lithium intercalation and deintercalation in a layered lithium nickel oxide structure using semi-grain canonical Monte Carlo approach, and we have also seen how the energy and composition of the system change in response to the varying chemical potential of lithium. Okay. Now, you can do some exercise also, you can see how varying temperature affects the delithiation behavior in the above simplified model. Okay. Or you can also obtain a similar plot as above by sweeping through the lithium chemical potential instead of vacancy chemical potential. Okay. So, this is the end of this session. Thank you.